Hello guys, welcome back to Digi Structures. Today we are going to be doing with frame analysis, frame structures, and this is an indeterminate frame. So we are going to be using the slope deflection method to solve this, and of course we can choose to use the moment distribution method, but in today's lecture, today's tutorial, we're using slope deflection. Now this small thing, it is enormous in calculation. So I understand that the use of software is so necessary these days. So what do we have here? The first thing when you are dealing with is a frame with that is indeterminate. You need to know whether it is a side sway, non-side sway, or non-side sway. Now for this, remember, move back to you can watch the video where I explained is the frame a side sway or a non-side sway. When you watch that, you can proceed with this. So SS now is equals to 2J. In that video you see this 2H plus F plus R plus M. Yes. So SS is equals to how many joints? 1, 2, 3, 4. 2 times 4 minus H plus F, no inch support, 0, plus fixed support, 1, 2, plus 1 roller support, 0 roller support, plus how many members? 1, 2, 3, 3 members. So SS is equals to 8 minus 4 plus 3, 7, and SS is equals to 1. It means that the restrictions have not done their job, so it is side sway. But let's look at the loading. The loading is 40 kN and it is applied. It's applied not applied at the center. You understand? It's not applied at the center. So because of it is not applied at the center, the loading is not symmetric. And because the loading is not symmetric, it adds to the side sway. So we can still call it a side sway frame. You understand? So this is a side sway frame. Side sway frame. So having established that, we can proceed. So invoking the slope deflection equation. Now M is equals to, before I do that, let me draw a diagram here to guide us. Let me draw it. Now, because it is swaying, let us assume it is swaying to the side, right? The first thing that we should draw is our elastic curve, which is also the same thing as our qualitative deflected shear. So to do that, of course, there is no slope. There is no slope. It's moving, so the deflection is this guy. Or let me not use this diagram. Let me draw another diagram. Let me use this diagram. Let me use this diagram. So qualitative deflection shape. Now because this is that's if this is A, this is B, this is C, this is D. So if this is A, this is B, this is C, this is D. There, of course, no slope. It's going to be 0. Then, because of the swayness, this is the new deformed position. The neutral axis deformed position, because it is a qualitative deflected shape. So, proceeding. Now, because we're assuming that the members are inextensible in a manner that they don't elongate, they don't elongate, do you understand? It means that, if that's the case, it means that this delta here will be the same as this delta here, so that the distance from here to here, which is a new BC distance, will be the same as the old BC distance. Do you understand? So, now that we know this, fact, we should now establish our chord rotation. Now, remember, in the slope deflection equation, we have a chord rotation symbol. So that is just going to be connecting our deformed axis, deformed end positions of our of each of our spans. So for this span, the deformed position for this end of A is this position. The deformed position for this end B will be this guy. So the line connecting it is our chord. The line connecting it is our chord. That's the first thing you should know. So this guy, for D, this is our deformed position. This is also our deformed position. And the line connecting it is our chord. Now, this chord that is now chord rotation. Chord rotation is now telling us now the angle it makes with the undeformed axis. This is the deformed one now. The angle. So we're taking it from the undeformed. So if we're taking it from the undeformed, it will now be phi AB, that will be here. It will now be phi DC, that will be here. That's the first thing we must establish. So now that we know this, we need to now apply this slope deflection equation. So, and for us to, even, let us not apply the slope deflection equation first. Let us solve for our chord rotation, because we'll need it so that when we are applying for our, when we're applying it to our slope deflection, it will be easy. We also need our fixed end moment. So chord rotation now. Chord rotations. Let's solve for them. Now for this, there will not be chord rotation because the deformed axis is the same as the undeformed axis, so there's no chord rotation. It's zero. That's the first thing. So bringing this triangle, drawing it there. Now, this is phi AB, this is this, and this was 7. So it means that this will be, now this was moving clockwise. So my convention, my sign convention is always positive is anti-clockwise, negative is clockwise. So if negative is clockwise, my chord rotation for AB will be equal to negative. The thing is that, think of it as tan theta is equals to opposite over adjacent, but theta is now so small. Do you feel me? So, and that theta we're doing the rotation in rad, not in angle, not in degrees. It will be rather be minus delta over 7. You understand? So tan theta of a theta that is so small is equals to theta, approximately equals to theta. So okay, an angle rather theta an angle. So chord rotation 2. No need to draw the diagram honestly, but for this guy, this will be equals to, now also clockwise. If you look at it, it's moving clockwise. So this guy is equals to delta minus delta over 5. So knowing this, we can put it here. Now phi AB will be also equals to phi BA. That one thing you should know. It will be equals to this. Phi DC will be also equals to phi CD, and it also equals to this. So let's put it here. Let's erase this, and let's get our fixed end moment. So obviously, fixed end moment for this guy will be 0. For this guy will be 0. But let's look at it. Fixed end moment, you assume that your support, the joint that are free to rotate. This guy is free to rotate. This guy is free to rotate. You you assume that those joints are fixed. So it means that when all those joints are fixed, everything is fixed, then you start competing for your fixed element. So for this guy, turning it in this direction like this, we are going to be having this. AB, FEM AB. For this, FEM BA. And since there's no force, once again, FEM AB will equals to FEM BA and will be equals to 0 kilonewton meters. Similarly, I won't waste time. FEM CD will also be equals to 0. FEM DC will be also equals to 0 kilonewton meters. So, the main guy is BC because it's an external force. External force, BC, FEM BC, FEM CB. So, the formula for if you go to your fixed moment, FEM BC will be equals to P, this is A and this is B, it will be P A B square over L square. And it will be equals to, once again, this is A, this is B, it will be equals to 40 times P times 3 times 4 square, which is 16, over L, which is 7 square, 7 times 7, 49. Of course, this is where, if you go to your fixed moments tables, this is where the orientation of the moment, but it is now up to you to tell us your convention, based on your convention, which one is positive of the two directions. But in our convention, we're using that anti-clockwise is positive. So that is why we're putting positive. So similarly, FEMCB, not similarly, there's a difference. Because of P A square B over L square, because of minus 40 times A 3 square 9 times 4 over 49. So that's 7 square. Where's the calculator? So 40 times 3 times 16 divided by 49. So 39.18 Newton meters. 40 times 9 times 4 divided by 49 equals to 29.3877 kilonewton meters. Yes. So FEMBC will be positive anti-clockwise, FEMCB will be clockwise negative. Do you understand? It is aligning, it is aligning, it is aligning. So let's erase this, let's put it here. AB is equal to FEMDA is equal to 0 kilonewton meters, which is also equal to FEMCD and DC. So FEMBC will be equal to 39.18 kilonewton meters. FEMCB will be equal to minus 29.3877 kilonewton meters. So when I'm stacking everything, it will be much more complicated to stack on. Now that we know our fixed moments, now that we know our chord rotations, we can now use the slope deflection equation. So, MAB equals to 2EI over 7, open bracket 2 theta A plus theta B minus, okay, plus, you know it's minus 3 alpha, minus 3 phi rather. But let me just write the formula first. Let me write the formula. This will be MAB is equals to 2EI over L, open bracket 2 theta A plus theta B minus 3 phi AB plus FEN AB. Yes. So, solving for this, MAB is equals to 2EI over 7, open bracket 2 theta A, which is going to be 0 because of the boundary condition of a fixed support. 0 theta B will be just theta B plus minus 3 times alpha phi AB is equals to minus delta over 7 plus FEN AB. FEN AB which equals to 0. So we need to include it. We need to include it basically. So, let's solve for this. Over 7, 2 theta EI over 7. Well, let's just use decimals. 0.285 theta B EI plus 3 over 7 times 2 over 7. That's times 2 over 7. That's 6 over 49, 0.1224. This EI, that's equation 1. So, of course, this will be from position. This will be your theta B. This will be theta C. B film. So, MBC will be equals to, we can erase this now. MBC will be equals to 2EI over 7, open bracket 2 theta B plus theta C. Now, phi BC is 0. Remember what I said. You know, the deformed position is straight, so for a straight line, the angle is 0. If you understand. So, like, relative to the, I mean, if the deformed position is the same as the undeformed, then it's 0. Nothing to, nothing to. So, plus FENBC. FENBC was 39.18. 39.18 units. So NBC will give us, when we solve this, NBC will give us 0.5714. Units. 0.5714 stabila plus 0.285 theta CEI plus 39.18. Let's say, let's put 3 there. 39.183. It was 39.1 when I calculated. So NBC will be 0.5714 theta BEI plus 0.285 theta CEI plus 39.183. That's our equation 2. We have to, now remember that we need to find theta b, we need to find theta c, and we need to find delta. So this is three things. So this is kinematically indeterminate by degree of 3, because we have 3 what's the name? What did they call it? We have 3 unknown, but there's something they call it. There's something they call it. I'll get back to it, but just in that it is 3 kinematically indeterminate of degree of 3. You understand? 3 unknowns. So MCB, MBC. Now MCA, MCB rather. MCB should be 2EI over 7. Now you get the slides in the description box, you just get it. I've solved it before, so I just, to be very fast, you need some theta c plus theta b minus 29.3877. So MCB equals to 0.5714 theta CEI plus 0.28571 theta BEI. When we solve for this, minus 29.3877. So MCB equals to 0.2857 5714 theta. Well, let's start with theta c. Oh, okay, 0.285 theta b ei plus 0.5714 theta cei minus 29.3877, which gives us equation 3. Right? Now, as MCB, now we have the next one. We have calculated MBC, calculated MCB. I mean, remember when we done the beam zone, there's a moment here, 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 there's a moment here. So that's what I've been doing basically. These are member end moments at the end of the members. So MEB, MBA, MCB, MBC rather. Now we've got MCB. Now what is MCD? MCD will be equals to now 2EI, the same slope deflection equation, over 5, open bracket, 2 theta c. Now theta d will be 0 automatically because of the boundary condition of the frame structure is a fixed support, no rotation. That is why the deflected shape started like hooked before it's now spread. So theta c, because of no rotation, 3 now plus minus 3 times the chord rotation for the other guy. The chord rotation for the other guy minus 3 times. You know that this guy is minus, so ideally it was minus 3 times the chord rotation, right? And the chord rotation is also minus delta over 5, so minus delta over So to give us MCD equals to 0.8 theta CEI plus 0.24 delta EI. Do you understand? So MCD is equals to 0.8 theta CEI plus 0.24 delta EI. That is it. 3, 4. Now we have the last equation, which is NDC. NDC 2AI over 5 on bracket 2 theta d, but theta d is 0 plus theta c plus the same chord rotation minus 3 times the chord rotation minus this over 5. So MDC equals to 2EI theta c over 5 plus 2EI over 5 times 3 delta over 5. So we have this equals to 0.4 theta c EI. When you get this 2 over 5 is 0.4 plus 0.24 delta EI. This, you have this. So, a minute. Now that we've gotten all our equations, we can clean this guy and we can explain something. I've explained it before, but I think if you watch my video on the beams, you see that you see how I got that the summation of moments at each joints that are free to rotate is always 0. You understand? There's not supposed to be moments at joints like that are free to rotate. Now you might be thinking, what I mean, there's a moment here that will get transferred to the joints. That is, we have moment at the joints that are free to rotate. How is that possible? Well, I tell you that we have 2 joint moments. I mean, right now, 2 member end moment that will eventually transfer to the joint, and to the joint. So these 2 moments, they are equal in magnitude but opposite in direction. So eventually they balance out and cancel. So we have no moment happening at the joint. But that's just it. But let me explain what I just said. So we're splitting the structure now. So we're assuming that all our member end moments are anti-clockwise. Our member end moments anti-clockwise. So of course there's a joint. So if this is anti-clockwise to the joints, it will be clockwise. To this, and transferring this to this, it will be clockwise. This was MBE rather. This will also be MBE. This was MBC rather. This will also be MBC. So it's the same thing, just that it's transferred. Similarly, this was MCB. So So transferring it, which is anti-clockwise, becomes clockwise, clockwise, anti-clockwise, clockwise. So this also is MCB. Now this was CD. This also becomes MCD, MCD, MDC. So that is just what I was trying to explain. So it means that the moment MBA plus MBC must be equal to 0 for us to establish that fact. Or if you don't want to think of it that way, you can say that summation of moment about this joint is equal to 0. That is anti-clockwise moment is equal to clockwise moment. So if this is clockwise plus clockwise is equals to, what is anti-clockwise? 0, nothing. There's no anti-clockwise for this joint. Like this joint. For this joint. This joint. So MBA plus MBC is equal to 0. MCB plus MCD is also equal to 0. So when we bring MBA was, okay, did we even do MBA? Okay, we didn't do MBA, but in the same similar fashion, MBA would be 0.55714 theta BEI, when you do it in the same manner. 1224 delta EI. So MBA plus MBC must be equal to 0. Let's do this first equation. So when we bring it here, that is 0.5714 theta BEI plus 0.1224 delta EI plus MBC and 0.5714 theta BEI plus 0.285 theta CEI plus 39.183 will be equals to 0. So solving this, we will now result to an equation that this guy will generate for us from this. We'll be having 1.14 when we collect this plus this will give us 1.1428 theta BEI. This or this alone give us plus 0.285 theta CEI plus this alone 0.1224 delta EI plus this 39.183 is equal to 0. That's the first thing. Second thing, we can keep this equation here. 1.1428 theta BEI plus 0.285 theta CEI plus 0.1224 delta EI plus 39.183 is equal to 0. That's the first thing. So doing the same thing for MCB plus MCD is equal to 0. I'm taking it from here, the MCB and MCB. MCB plus MCB equals to 0. MCB is 0.285. 0.285 theta BEI plus 0.5714 theta CEI minus 29.3877 plus MCD. MCD is 0.8 theta CEI plus 0.24 delta EI equals to 0. So this plus this plus, okay, that has gone. We're having this alone 0.285 theta BEI plus this will give me 1.3714 theta CEI plus this guy will give me 0.24 delta EI minus 29.3877 equals to 0. So bringing it to that side also. 0.285 theta BEI plus 1.3714 theta CEI plus 0.24 delta EI minus 29.3877 equals to 0. Now we have three unknowns, theta B, theta C, and delta, which is needed to get our moment. Theta C, theta B. Yes, we have three unknowns. So we need three equations. Where can this particular new equation come from? Where can it come from? So we're going to leave these guys. These guys are the main thing, because it's where we are picking, we're making new equations and we're substituting these guys into those equations. So I'm going to leave them. We can erase your guy. So now in this diagram, let us do something. Let us apply summation fx. Well, let us first draw the external reactions acting on these frames. External reactions from the support. External reaction from the support acting on this frame. Let us draw it. We're going to be having one here. I'm going to be having one here, and of course the MAB that we'll calculate, let's say this anti-clockwise, is going to be here, because that will be the moment that will act there. So MAB and MDC, this one will be, since it's D, this one will be DY, and will be an X force, and it will be an horizontal force, which is DX. Let us call it SDX. Let us call this horizontal force here SAX. And let's just call this one EY. Let's just call this one AB. Yes. So let us apply summation fx to this entire structure. To apply summation fx to this entire structure, you can see that I like to be smarter. I don't want to use negative, so I just assume that okay, SX1 is going here, the other horizontal force is going there, so it will make it smooth for me. So SAX, that is right is equals to left, simply put, equals to 0. STX, or left is equals to right, anyone. So I can now do something very wonderful. I know that this is what I have, right? SAX is equal to SDX. This is my new equation. SAX is equal to SDX, right? I can do something interesting. I can detach my structure again. Let me detach it. Of course, there will be a moment here, there will be a moment here, there will be a moment here, anti-clockwise, moment here. And the SAX was acting in this direction while neglecting the Y forces. For now, STX, SAX, anti-clockwise, anti-clockwise. So this will be NAB, this will be NBA, this will be MCD, this will be MDC. Right? So, what is next? We want to make this SAX and SDX in terms of course, there will be a force here. There will be a force here, right? There will be a force here. Let's just assume any rubbish. Because let's just assume the equilibrium equation will correct it for you. You understand? The equilibrium equation would correct it for you. When it gives you negative, it tells you that what you assume is wrong is that you correct it or use the negative in the equation. So, applying summation M, this is A, this is B. Now, I will be wise if I apply my summation M about B. Because if I apply my summation M about B, I won't have to consider this rubbish force that I assume. But I'll be considering the main point of interest, SAX. I mean, when I apply it at B, SAX will be useful. SAX will act, but BX will not act because that's the same location. You can't have the perpendicular distance is 0. Do you understand? So if I apply about B, it will be SAX times 7. SAX times 7. Okay, applying. Let me do it here. Summation M. Demarcating this. Summation M B equals to 0. Summation M B of B is equal to 0. Let's apply it. MBBA as per BA. So SAX times 7 will be equals to, anti-clockwise is equals to clockwise. So this is clockwise, SAX times 7, which other one is clockwise, nothing else, remaining anti-clockwise is equals to MBA plus MAB, right? So SAX is equals to MBA plus MAB over 7, right? Right? Similarly, for this guy, summation NCCD is equals to 0. Applying it about this guy, this point. So SDX, MD, everything is anti-clockwise. So SDX times 5 plus MDC plus MCD is equals to 0. So SDX is equals to minus MDC minus MCD over 5. Over 5. You understand? So I cannot equate these two of them. Equating these two, I would have MBA plus MAB plus 7 is equals to minus MDC minus MCD over 5. So 5 MBA plus 5 MAB equals to minus 7 MDC minus 7 MCD. Can you see? Now I have to now start applying, substituting all these things. inside the equation. So interesting, right? So let's do it. 5. Let's remove this guy. I don't need it anymore. 5 MBA 0.5714 theta BEI plus 0.1224 delta EI plus 5 MAB 0.285 theta BEI plus 0.1224 delta EI is now equals to minus 7 NDC 0.4 theta CEI plus 0.24 theta EI minus 7 MCD 0.8 theta CEI plus 0.24 delta EI. So this is my equation from here to here, everything equals to, don't forget. So once I solve that, once I collect like terms, I'll be having this. I'll be having this equation, which is 4 points. I'll be having 4.2855 theta BEI plus 8.4 theta CEI plus 4.584 delta EI is equals to 0. So bring out your calculators a minute. Okay. All right. Okay. Bring out your calculators. Let's spread this. Next, you will make theta b. When you press it equals to x, you make theta CEI equals to y, and you make delta EI is equals to z. So it will give you the simultaneous equation that you are very familiar with, like in terms of x, y, z. That is 3D systems. So eventually, when you press it on your calculator, you'll be having theta BEI, which is equals to x is equals to theta BEI, which is equals to minus 40.14. Y is equals to theta CEI 34.188. Z is equals to delta EI 25.119. So, knowing all this, we can now start substituting it back into all these equations so that we can get our moments for each. So, starting with this. Starting with MAB, 0.285 times theta BEI minus 40.14 plus 0.1224 times delta EI minus 25.199. What do we have? When we press our calculator, we have minus 14.54 kilonewton meters. Right? Okay. Now that we know that our MEB is equals to minus 14.54 kilonewton meters. Now, what is MBE? MBE will be 0.5714 times theta BEI, which is X, plus 0.1224 delta EI, which is minus 25.199, I guess. MBE. Sorry, 119. The other ones are 119, but it will give you the right answer. MBE. So MBE is equal to minus 26.0105 kilonewton meters. So MBA will be equals to minus 26.0105 kilonewton meters. So MBC is automatically, because when you remember that equation MBC plus MB is equals to 0, MBC is automatically 26.0105 kilonewton meters. Right? Now, MCB. MCB will be equals to 0.285 theta BEI minus 40.14 plus 0.5714 times theta CEI 34.188 minus 29.3877. That will give you MCB from here. So at the end of the day, you get what's the name? You get minus 21.3218 kilonewton meter. So if you know MCB, you know MCD. Minus 21.3218 kilonewton meters. MC equals to 21.3218 kilonewton meters. Now we have MD. We have MDC. MDC 2EI over 5. Okay, so we have the equation already. MDC is equals to 0.4 times theta CEI is 34.188 plus 0.24 times delta EI 0.119. So MDC equals to positive 7.646 kilonewton meters. So MDC 7.646 kilonewton meters. Now we have our moment. We need to start our shear force and our bending moments. Diagrams. But before we get our shear force and bending moment diagrams, we need to get our end shears, our internal forces. Do you understand? We now want to redraw our diagram in a much better way. So, here we have this. Here we have this. Here we have this. So, now we have MAB is equals to minus 14. AB will be here. It will be minus 14, which is clockwise. Minus was clockwise. 14.54. The other guy is BA. BA will be minus clockwise. 14.54. This guy here will be. Now I can choose to neglect my joints because there is no force acting on the joints. If there was a force acting on the joint, I would need to consider my joints so I can be so careful. But now I don't need to be really careful. I can just transfer it to the other member since there's no force acting on the joint, right? So this guy MCB was not clockwise but anti-clockwise. Okay, that's BC. Okay, mistake. BC is anti-clockwise, yes, that's 6.065. 26.0105. Oh, what am I doing? This one too is 26.0105. 26.0105. So 26.0105. So the other guy is 26.0105. The other guy is 21.32, which is CB. CB minus 21 clockwise. 21. 212. CD is clockwise and anti-clockwise. 21.3218. DC is anti-clockwise. 7.64. And the reaction. When we assume the SX, we assume it. We assume it. It doesn't matter. Right. We assume. x direction, y direction. I'm assuming directions. Yes. So we call this AY. We call this AX. We call this A. We call this AXBA. We call this AYB. Sorry, BX. BA. We call this BYBA. We call this BX BC. We call this BY BC. Make this much more clear. This is an arrow. So no arrow. So let's call this B and C instead now. Let's call this X CD rather CYC. Now this is CY CD. This is CX CD. This is the first. So and of course this is DY. This is DX. Starting with this. Applying equilibrium equations to each of these members now. Starting with AB. We're applying equilibrium equation. We're going to be having 26 points. We're applying the summation of moment at B is equals to 0. So we're having 26.0105 times, if it's already a moment, we're having 14.54. We'll be having 8x times 7. All of it equals to 0. You might be asking, why is it like this? Because summation of moments about B is just anti-clockwise equals to clockwise. Just have that at the back of the mind. So 26.0105. 26.0105 plus 14.5. X would be minus 5.7 minus 5.79 kilometers. Then it means that Bx will be when we apply summation fx equals to 0, Bx Ba will now be equals to minus 5.79 kilometers also. Because okay, it was in the same direction that we assumed. So by using the direction we assume as reference, so X, BE, AX is also in that direction. So since we now see summation fx equals to 0, it means right is equals to left. And since all we have here is left, it's just the left is equals to right and right is 0. So AX plus bxba is equals to 0. bxba is equals to minus ax, and minus ax is basically 5.79 kilonewtons. So we got in this direction correct, but we failed ax. So we move to to number B. Now, which we will be thinking, why didn't you apply summation Fy? There's nothing, okay. We cannot get our values now if we just apply summation Fy is equals to 0. Why did I say that? Summation Fy equals to 0, it will be downward is equals to upward, so Ay is equals to By Be. But we don't have any value yet, but we need to go and find it. So we can find it from this guy. BC. Now I'm doing BC. We need BC. So okay. So BC. Now BC is equals to for BC we're going to be saying some, of course, the same applying the equilibrium equations, right? Summation of moments about B is equals to 0. So we're having 26.015. Plus 7 CYB CYCB is equals to 40 times 3. But we have 21 points. Plus 21.3212. I mean, anti-clockwise 26.015. Another anti-clockwise CYCB. Imagine this as a ball. 40.3 clockwise. 21.3212 clockwise. Do you understand? So solving this we get get 96.686788. Okay. CYC, SYC, to be 16.4729 kilonewtons. So let me cross check. Yes. So from equilibrium equations, applying summation Fy is equals to 0. We have then CYCB plus BYBC is equals to 0. So CY and BYBC will be equals to, so 0 equals to 40. Plus 40. So now be 40 minus 16.4. So first 40 minus 16.402, 33.5